If you're a chemist, you might be concerned about how much energy it takes to heat substances, pure substances. This is known as the specific heat of this substance. And this will be the topic of this screencast. We'll ask what it is, we'll take a look at that wordy textbook definition and try to convert it into a real-life definition or even a lame synonym, and we'll go ahead and think about what it's composed of, how it relates to heat, which is, I guess, a big part of it, temperature, and how much you're heating. This is Screencast 12.5. We'll ask ourselves, what can specific heat tell us in general? How can we apply it to the real world? And we'll use it to solve a typical problem using specific heat. One of the cool things you can do with it is you can identify unknown substances with it, since it is a specific property of a substance. Okay, it's the amount of heat necessary to heat a gram of water by 1 degree Celsius. Not a liter, just a gram. That would be 20 drops of water. It would also be 1 milliliter of water, since the density is 1 gram for every milliliter by definition. It's specific heat. Where is it? It's in there, right there, C. And here's how it relates to things like heat, temperature, and mass. The amount of heat necessary to heat something up depends on, well, how much you're heating, right? More will take more heat. How heatable it is, that's, the specific heat. Some things heat up very easily, like, say, aluminum. Other things heat up with great difficulty, like water. It's an intrinsic property of that substance. And it depends on how hot you want to get it. That's the change in temperature. There's the actual number for liquid water, 4.184 joules for every gram for every degree Celsius. These units are perfectly set up so that you can solve problems with it. And here's some other numbers, just so you can see some familiar units for joules per gram degree Celsius. Water tends to dominate, particularly liquid water. It takes 4 joules to heat 1 gram, 1 degree Celsius. Far less for all these other substances. Note also that it depends on what phase you're in. So if you're going from, say, minus 10 degrees Celsius to plus 10 degrees Celsius, well, that's a more complicated problem because it's going to be easier to heat up the liquid water than it is to heat up the ice. Let's do a simple problem where there is no phase change involved. Let's make a cup of tea. You're going to take 1 cup, that's 237 mils. Notice that's also 237 grams because it's water. And you're going to take it from room temperature, put it in the kettle, and take it off once it boils. We'll consider this to be all taking place in the liquid phase, and let's solve this problem. They want to know the heat, that's Q, so it's a direct plug-in. M, the mass. We said before it's 237 grams since the density is 1. Specific heat, there it is for liquid water. And 100 degrees Celsius from 25, you should recognize that the change in temperature is 75 degrees Celsius. If I put the units here, and I really should, you'd see that they all cancel nicely and they just spit out joules. And it's about 74,000 joules to do that. You should be able to convert that to things like nutritional calories, etc., given the conversion factor. I know, Pablo, I'll get you your cat food in a minute. That was Screencast 12.5.